Okay, here we go again, Chapter 6, States of Matter. Make sure you're looking at the learning objectives as you're going through this chapter. It's got a lot of different things in it, so make sure you're checking those off and understanding those so that when you get to the test you know each of those learning objectives. I've put a Gold's Gym ball here that's sort of deflating because we're going to be talking about gas and liquid and solids. So here we go. Solids make up most of the periodic table at room temperature. We only have two liquids. Those are metal, which is mercury, which is also called quicksilver, and the nonmetal, bromine, which is a reddish-brown liquid. Okay, the gases at room temperature on the periodic table are nitrogen, oxygen, fluorine, chlorine, and then the noble gases. So helium, neon, argon, krypton, xenon, and radon. So it's probably easier to memorize which ones are liquids and which ones are gases at room temperature than it is solids, because everything else is solid. Oh, I forgot one on the noble gases, or on the gases, and that's hydrogen. So don't forget hydrogen. Okay, so we've got the ones basically part of Braunhilfe, are the noble gases, not including bromine, because bromine is a liquid, that we need to recognize. Now, when we talk about changing the volume, if you think about it, that Gold's Gym ball that I had, if I put it in the freezer, what would happen to it? Well, it would shrink even more. If I put it out in the hot sun, it would grow or expand. So we call this thermal expansion. So thermal expansion is basically the change in volume resulting from temperature change. Just like when we have a thermometer, we can draw our little Celsius simple thermometer here. And now they actually have an alcohol-based center that's red. When it was mercury, it was silver. But as the temperature gets hot, you see that red line go up, or the red snake grow is what my little kids used to say. So that's because of thermal expansion. So the hotter it is, the higher the red goes. The colder it is, it shrinks in response. Okay, we're going to go back a little bit to density. We talked about that a while ago, so hopefully towards the beginning, I believe. But density is just that. Density is mass divided by volume. And I showed you that it's basically a heart. You can make a heart with your hands and cut it in half, and the top is the M and the bottom is the V, so I help you remember how it goes. That you can solve for any part of this. You could solve for volume, you could solve for mass, you could solve for density, and you need to be able to. So let's take a simple example. Say that we had given to us that we had a sample that had a mass equal to 0.602 grams. And we had a volume equal to 500.0 milliliters. Well, in order to find the density for that, all I need to do is take the mass and divide it by my volume and plug it through my calculator, and I should end up with 0.00120 grams per milliliter, also known as 1.2 times 10 to the negative third, reviewing that really quick in scientific notation. So these would be my answers. Two significant figures. I actually should have carried that zero down here to say three significant figures. Okay, so pretty easy. I can also do it if I'm given, for instance, say that I was given density. So here I'm being given density is equal to 0.762 grams per milliliter. And I wanted to find out the volume if I had a mass of 78.5 grams. Well, then I just take that 78.5 grams divided by that 0.762 grams per milliliter. Here our grams would cancel out and our milliliters would be 1 over 1 over milliliters, so we'd get milliliters. And my volume would, to 3 significant figures, plugging through my calculator, be 103. So I guess I should have squared that up there. So you need to be able to go back and forth and figure out any density or part of a density problem. Okay, the next thing that we need to talk about is kinetic molecular theory. I like to call these toddler rules, and you'll understand why. There are 5 rules, and basically a toddler is considered anybody under 5. So that helps me to remember this. We'll go step by step and I'll show you how I remember. Okay, so the first rule is matter is composed of tiny particles called molecules. Well, toddlers are small, very small compared to bigger people, right? Okay, so the second one is the particles are on constant straight line motion and therefore possess kinetic energy. Well, think about a toddler. If you ever watched a toddler, they're in constant motion. They don't seem to pass out or stop until they pass out, is what I was meant to say. They just keep going. They seem to have their attention drawn to one thing. They go over and they touch that, and then they get distracted and go to something else. So that's what it's toddler rule number 2. The next rule is that the particles possess potential energy as a result of attracting or repelling each other. So if you remember a kid, they just don't have the ability to, they have potential. They haven't reached it yet. But they are always attracting some people, and other people don't like toddlers, so they're repelled. But they have the potential of attracting or repelling other people. It's just potential at this point. Remember, the toddlers, they just don't have any boundaries, I guess I would say. You know, they'll blurt out just what they see. You know, that man has fuzzy hair, that girl has a big nose. You know, they aren't attracted or repelled by anybody. They're just curious. Okay, the fourth toddler rule, or kinetic molecular theory, is that the average particle speed increases as the temperature increases. Now think about this. In the wintertime, the kids just play inside, just sort of mellowish. But as summer comes, or as it's nice outside, they want to be outside, and they're going and going and going and going. As temperature increases, they want to be outside. They want to do stuff. Okay, so the last one basically says the particles transfer energy from one to another during a collision in which no net energy is lost. Toddlers bump into everything. As long as nobody's watching, there's no crying, and they just get up and go on. So their collisions are sort of what we call elastic. In other words, no net energy is lost. They just keep going and going and going. Sort of like the Energizer Bunny. Okay, so kinetic energy is often known as the energy of motion. And to get kinetic energy, we have the equation. Kinetic energy is equal to 1/2 the mass times the velocity squared. So velocity is usually given in a measurement of length divided by a measurement of time. You can use this kinetic energy equation to compare samples, to find out which one has more kinetic energy. We're just going to do an example where we're just finding the kinetic energy of one. So if I have a particle with a mass of 3 grams moving at a speed of 15 centimeters per second, then what I do to find the kinetic energy is plug it into the kinetic equation above, where I've got my 1/2 times my mass times my velocity squared. So when I plug that through my calculator, I end up with 338 to 3 sig figs grams per centimeter squared divided by second squared. And so that is equal to my kinetic energy for that particle going that speed. So kinetic energy, again, energy of motion. So you need to know that and how to figure for it. So potential energy, different from kinetic, is the result from attractions or repulsions of particles for one another. Some of these we already know, like gravitational attraction of the Earth and the behavior of the poles of the two magnets brought near each other. In each of these examples, the size of the force of the potential energy depends on the separation distance. The same behavior is found for potential energy in atom-sized particles. So the potential energy of attraction increases as separation increases, whereas the potential energy of repulsion decreases as separation increases. So if we look at this, we have a couple of forces that we need to worry about. And those are the cohesive force and the disruptive force. So cohesive force is associated with potential energy. This is potential energy. Let me get a pen here, potential. And disruptive is more associated with kinetic energy. So I just abbreviate KE, and potential energy, of course, is PE. Haha, no, we're not running a mile. Okay, so this cohesive, of course, is attractive forces, and disruptive forces are resulting of motion, so I'm disrupting things. Now, disruptive forces tend to scatter particles and make them independent of each other. So think about moving around and jumping around. Cohesive forces have the opposite effect. They're sort of coming together and have a relative stability, and cohesive meaning, like, you know, if you're cohesive, you bind together or bond together. Okay, so hopefully that will help. Now remember, cohesive forces are dependent on, are independent of temperature because they involve inner particle attractions. Disruptive forces increase with temperature because they arise from particle motion, which increases with temperature. That explains that temperature plays an important role when we determine the state of matter that we'll be finding. And we'll talk about states next time. See you in class.